right into the camera.
Eh.
Oh my god. I'm so sorry, guys.
I mean, if someone was, they watch the video if they weren't here in person or if they need to make something up, in which case they'd hear your hiccups anyway if they were here.
That's so valid.
And I'm recording the same lecture 3 times, so if they really wanted to, they could just watch one of the 2 takes that don't have hiccup.
So basically, they're the problem.
I'm not saying anyone is a problem, which includes you when you're hiccuping. There is no problem. I'd say the only problem would be if my dog is here, because hiccups scare her.
Oh.
I don't know why.
It's weird.
Lost my train of thought. How y'all doing? That's fair. That is also valid as just a perpetual response, because I'm also perpetually tired. If you ask me how I'm doing, key answers are usually tired and hungry, and thirsty, dehydrated, often bored and distracted. Anyway.
I took a calc quiz if that answers that.
Yikes! Well, let's talk about anything else then. This is an algebra-based class, not a calculus-based one. Today we are going to look at more projectile motion and more 2-dimensional vectors. Does anyone have any questions, concerns, needs, etc. before we get started? All right. So, last time, as part of our introduction to 2D motion and as part of a continuation of projectile motion, we looked at this situation where we were launching a cannonball off of a cliff. A cannonball is being fired at 100 meters per second at 75 degrees. This object is moving 2-dimensionally. It's moving both in the x and the y simultaneously. But that 100 meters per second is on an angle, meaning that that 100 is itself neither completely x nor completely y. It's literally somewhere in the middle. And we actually know where it is in the middle because that's the role that the angle serves. It tells us, it gives us an idea of how much of that 100 is ending up in either axis. And last time, come on, dramatic reveal, we actually found how much is in each axis. We used our trig here, SOHCAHTOA, to find that the x component of this vector is 25.9 and the y component is 96.6. Is that correct? Does that sound familiar? Okay, I'll make sure I remember them right. And what those represent is, separately, how much of that 100 is ending up in either axis. How much of a vector ends up in either of its component axes depends entirely on the angle. This same 100 meters per second could create very different component legs depending on that angle. And as a pro tip / fun fact, 45 degrees always maximizes the relationship between x and y. So if you are ever trying to throw as far as you can, try to throw at 45 degrees. But today we're looking at 75 degrees. Last time we used this as trig practice to divide this triangle up. We're going to finish out the question today as a little more projectile motion review. But before that, just as one more quick aside, I'm going to point out that all the information right here represents 2 different ways to write down 2-dimensional vectors. So the hypotenuse of that triangle is a 2D vector because it is a vector that points in more than one axis at once. And any 2D vector has 2 different ways it can be written. You can write 2D vectors much as you may have written them in past math and geometry classes in component form, those being the legs that we found last time. This represents the components of the triangle, the magnitude in the x, the magnitude in the y, that create the 100 meters per second hypotenuse. That is one way to write out two-dimensional vectors. And really one-dimensional vectors can be written the same way. Like if you were traveling 5 meters per second in the x-axis, the y component would just be 0. So you can write vectors in this component style. But separately, since vectors are defined as a magnitude and a direction, the other way to write them is literally magnitude and direction. These two things mean the same thing, mathematically speaking. Notice that both combined basically tell us everything about the triangle that we've formed, but they are both valid ways of describing any given vector. And oftentimes we will need to find one of them or both of them, depending on exactly what you've been asked for in a question. Does that sound okay as a frame of reference? Okay. Now, in this particular case, we have both of these versions already. We used the magnitude and direction version to find the component version, and that's because given the question that's being asked here, we needed the components separated into axes so that we can now examine and do math in the two axes separately. Because the actual question here, I didn't actually address the question being asked, I just used the trig for practice. The actual question here is, this cannon is being fired, and this one's explosive. The cannonball is going to detonate 5 seconds after launch. We want to know, where is it going to blow up? Where is it going to be after 5 seconds when it explodes? People who operate fireworks have to do this math all the time. You want to make sure that they go off up there and not in your neighbor's yard. So, we want to know where this thing is going to go off. Let's list all the things that all the numbers that we have access to. We've already divided up our initial x and y velocities. We've already done that work, so that'll save us a little bit of time. Bless you. So, those are our initial launch speeds in each axis separately. Now, if this is a projectile, not rocket powered, it's going to get launched and then gravity is going to take over, what does that tell us about its acceleration in midair? Say again?
It's decreasing.
All right, acceleration is going to be 9.8. Which axis is that in? Very good. What does that tell us about the x acceleration? Sorry?
It won't change.
The x acceleration won't change, and also the x velocity won't change. Because if you are a projectile, if you are falling, x acceleration is automatically 0. Oops. Since this is a cannonball, which does not have a thruster, it is a projectile, therefore, these are your two accelerations. You're falling down in the y, and nothing is happening in the x. No, there's no acceleration in the x. That is true of any projectile that is not flying, gliding, or parachuting. Now, questions so far? Okay. Our goal is to find our ending positions. To that end, we actually do know our starting position. if we consider this spot down here to be our origin, the cannonball is actually being fired 15 meters up at a position of 0, 15. Now we do have to take that into account, because like if you can throw something 100 feet into the air, good for you, but if you start on the ground, it will get to 100 feet. If you start 15 feet up, it's going to get to 115 feet. So you do have to note your starting height. So in the x-axis, I'm trying to list a column of x's and a column of y's. In the x-axis, our initial position is 0. In the y-axis, our initial position is 15. And the last piece of information we were given is the time before kaboom. We're going to spend 5 seconds in the air. So, what we're actually after here in both axes is final position, xf and yf. So given all the things we know and what we're after, what formula or formulas are good options to begin exploring? Formula 3 is a pretty good bet. It does describe motion over time, where there may or may not be acceleration. So let's examine Formula 3. Displacement equals initial velocity times time plus 1/2 times acceleration times time squared. Now, motion in two axes happens simultaneously, but generally speaking, separately. So, as I said before, we do have to do this equation once for our x's and then a separate time for our y's. So, I've labeled this is going to be our x work. Now I'm going to plug in only stuff from the x column. Delta x translates to x final minus x initial. That's what delta anything translates to. And final is what we want. We want to know where this thing ends up after 5 seconds. Initial, we already know, is 0. And minus 0 kind of does nothing, so that'll just go away in a minute. So that's the first part. Next, VIX, we've already found to be 25.9, 5 seconds in the air, plus 1/2 times our acceleration in the x-axis of 0, and then 5 squared. So, acceleration of 0 means that entire tail piece is just going to go away. Which means that you can legally use Formula 1 here. The caveat for Formula 1 is you can't be accelerating, and that is true in the x-axis. And again, to briefly review, just this part, delta x equals VI times time. This part by itself, if this part goes away, is Formula 1, just rearranged. So Formula 1 is the more specified version of this. This is the more general case, which is usually why Formula 3 is a pretty good bet if you're not sure what type of motion formula to use, because it kind of works in place of Formula 1, but we keep Formula around because it's a definition and we have to define all our terms. Now, back to this. XF is our only unknown, so we are good to solve for it. Several zeros are just going to fall away here, which is always nice. And memory serves, XF should be 129.5 meters. So that is the final X location of where this thing goes off. So within 5 seconds, this thing has enough time and enough speed to move this far forwards. Yes?
If you had a question like this on the test, would you have like a range of acceptable answers?
Yes. If you rounded to 130, that is fine. If you wrote down 135, I would look over your work and see where you rounded. But as long as it's just rounding, I take it. Feel okay for this? Feel okay for the x-axis? All right. Now in the y-axis, we use the same formula, but plugging in only y stuff. Delta y equals diy times t plus 1/2 ay t squared. Now, two things are going to be different in this version. One, a doesn't equal 0, so there's going to be slightly more math involved. B, in the x-axis, we're only really moving in one direction, and that's forward. In the y-axis, there are things that point up and then separately things that point down, even within the same axis. So for what we're about to do, keeping track of directions, and therefore positives and negatives, is very important. So I'll elaborate on vector direction as I'm filling things in. Delta y is, again, final minus initial. So yf minus yi. Yf's what we want to know, and what we already know is that this thing is beginning at the top of a 15-meter tall cliff. So the initial position is positive 15. So we're going to plug in a positive 15. But there was already a negative sign there. So that's why it looks like a negative. It's technically minus a positive. Does that track? Okay. And we do have to do this right to make sure we're adjusting the height correctly. Next, VIY times t. The initial y velocity points up. So we'll put in a normal positive number. We would only put it in negative if the cannon was pointed this way. So 96.6 times 5, and then plus 1/2 times our acceleration times time squared. This is the main negative that we have to install manually, because even though the cannon points up, gravity points down. So do make sure that that 9.8 is negative, and then times 5 squared. All right so far? All right. Try to simplify one bit at a time. Yf minus 15 equals 483 minus 122.5 and overall that should give us a final answer of positive 375.5. Two terms on this side would be about 360, but we have to add 15 to both sides because of the initial height offset. Questions getting to that number? All right. So these two numbers represent the distance the final position of the cannonball in each axis. Final x position is 129.5. Final y position is 375.5. So that's the coordinate location of where boom happens. And together, those coordinates could be used to also describe straight line distance from origin to its final location. Yes, Bill. All right. Once again, very useful historic math after humans invented projectile weaponry and gunpowder. Because again, you want to make sure to not miss your target and to not blow up your own boat. Yes?
Can you show again on the graph what that, like
This?
the coordinates that we just made, like
Oh,
what it goes back to? Like where, what is,
so here's origin, 0, 0. This position would be 129.5, 375.5. So about 130 scaled away in the X. And this drawing is not to scale at all. 375.5 in the Y.
Could you show again how you split up the 100 meters per second between the X and the Y?
Yeah, sure. We did that utilizing our trigonometry because we knew 100 meters per second and we know it's pointing at a 75-degree angle. And that information allows us to take that initial measurement and turn it into a right triangle. My handwriting is worse than normal today. So, any vector, if you know its magnitude and direction, can be written as a triangle like this. The magnitude is always the hypotenuse, and the direction is always that hypotenuse's angle from one of its legs. So, if I draw the picture like this, I would recommend using SOHCAHTOA to help find the missing two sides. So to quickly review, to do SOHCAHTOA, you need to know opposite, adjacent, and hypotenuse. So from the known angle of 75 degrees, which of our two mystery legs is the opposite leg? Correct? Opposite is always the leg that is not touching the angle in question. And hypotenuse is always its own separate category, which leaves the X leg as the adjacent, because it's the angle, it's the leg touching the angle that isn't already the hypotenuse. So, in this case, Y is op, X is adjacent. That will not always necessarily be true. X is not always adjacent, Y is not always opposite. It depends on which mystery angle you're working from. You're never going to work from the right angle, because trig is not designed to work that way. If you pop 90 degrees into any of these, things stop working. Basically, the trig function would give you a 1, and then it doesn't continue from there. So we always work from one of the two acute angles. From this angle's perspective, Y is op and X is adjacent, but that's reversed from this one's perspective. So that's 75, this would be 15 degrees. So from this one's perspective, that would be flipped, but the hypotenuse remains the same. So one reason drawing pictures is always important. You need to make sure you write down which angle you know and what is opposite and adjacent from its current perspective. Once you've determined that, you've then figured out what legs live where in these things, and you can pick one of them, like sine 75, opposite over hypotenuse, that's X over 100 to solve for X. Yes?
So does trig only work on like 90-degree angles?
Yes. These functions only work if the triangle has one 90-degree angle in it, but theta will never be the 90-degree angle. It has to be there, but it's not the one you're operating from the perspective of. Part of the reason for that is, I'm just going to draw a separate angle here. From the 90-degree angle's perspective, the hypotenuse is opposite, and that breaks everything. have to pick adjacent. The math is not designed to work from the 90-degree angles perspective. It has to be there, but it's never going to be the theta. And conveniently in this class, we're only really going to ever work with right triangles because conveniently x is always perpendicular to y by definition. I'm never going to give you an isosceles in here unless the point is to turn it into two right triangles. Does that answer your question? How you guys feel? All right. If you haven't had lab yet this week, make sure to bring these notes with you because we are doing cannons and projectile motion. Last thing we're going to do today is I want to try to apply some more of this trig information to help with different types of 2D vector scenarios because this is not the only kind of 2D vector scenario. Yes?
Just the sine of 75, wouldn't that be y?
No, you're right. Thank you. Please call me out if I ever do that by accident. And likewise then, cos of 75 should be x over 100. And tan 75 would be y over x. Feel good before moving on? All right. So, that's not, no, it's good information. But, this is the beginning of our study of two-dimensional vectors as a whole. Launching things off of cliffs, projectile motion is not the only time where things move in both axes at once. Because really, pretty much any motion can be described as 2D, because even if you are moving only in the x, like if you are just moving 5 meters per second forward, you do have a y component. That y component is just 0. So really any vector can be written two-dimensionally, even if it does point in one of the key axes. So pretty much any vector, as long as it has a direction, can be two-dimensional. So we need to be able to describe pretty much any vector as two-dimensionally, and we need to be able to add vectors two-dimensionally. So in addition to just using trig to break down triangles, we're now also going to begin breaking down and adding vectors together where they possibly point in multiple axes at once. For this type of question, I recommend even more than normal drawing pictures, because this is basically just geometry applied to the real world, and in geometry, pretty much always need a picture to make sure you're putting everything in the right place. So, for some practice, we're going to look at sports. A quarterback is going to start on this line of scrimmage, denoted with the dotted red line there. We'll define our starting point origin as this black dot labeled 0, 0. Someone's going to say hike, and the ball is going to be taken 10 yards straight backwards, perpendicularly to this line. So I'm beginning our picture with this is pretty much the only time I'm going to use yards instead of meters, with a 10-yard line, quote unquote, backwards. I'm defining backwards as -x for today. Perpendicular to the line of scrimmage, as if we were watching this from the stands. any part need to be written bigger?
Part of the dot.
Of this?
This.
Yeah, Bradley. That's 0, 0, because that is the origin of our system. So, hike, backwards. 10 yards feels like a lot to step backwards, but next thing that happens is this person is going to run 15 meters parallel to the line. So they've stepped back, and now they're scaling in some direction. I'm writing here positive y for 15 meters. And then the ball is going to get thrown 50 meters forward. Backward meant negative x. Forward, therefore, in the opposite direction, is going to mean positive x. Does this look like football plays that you guys have seen before? At least, a little bit. All right. So, we have 3 vectors here, and we need to add them together to figure out where this thing lands. And as I said earlier, there's 2 ways you can write any vector. First is in its component form, and second is in its magnitude and direction form. We're going to find both of those. First, for component form, we're going to take all 3 of these vectors and we're going to add them together. So this is the part of the course that I refer to as vector addition. Literally, it's just taking separate vectors and adding them together into a single vector. That single vector here being the distance from start to finish. So we're going to take all 3 of those lines and add them up into the green line. Now, in order to add vectors together, 1, I always recommend drawing a picture. 2, I always recommend in your picture drawing the vectors what I call tip to tail. That is one right after the other. You draw one from start to finish, and then on the arrowhead of the one you just finished is where you start the next one. In the case of this, that does kind of already describe the motion that's happening here, but in other examples, where the situation itself does not follow a literal path like this, it's important to remember tip to tail. Draw a picture, tip to tail. List out the numbers that you have and make it clear what axis that they're in. Because in order to add vectors, you have to add the x components together and then separately the y components together. So like with the other 2D work that we were just doing, the axes themselves take place simultaneously, but we don't mix the numbers together. So we've got 2 x-axis vectors here and 1 y-axis vector. And when I add vectors, I tend to just literally add them. I write out the whole thing, x and y. And do good old-fashioned kindergarten addition. Once again, though, the axes themselves don't mix. So we've got 1 column here for x. So -10 plus 0 plus 50 gives us 40. And then 0 plus 5 plus 0 is 5. 5? It's 15. Whoops. 0 plus 15 plus 0 is 15. Sorry. And that is the component form of our final answer. Vector addition can be pretty straightforward when there's no trig to do yet. So, it's literally, the hardest part of this stage is just making sure you don't mix your axes. The second hardest part of this stage is making sure that you point everything in the correct direction within its own axis. Because in this specific scenario, the 10 and the 50 point in opposite directions within the x-axis. They're working against each other. So they don't add to 60, they add to 40. And this tells us, if we wanted to know the coordinate location of this spot, it would be 40, 15. Arriving at that answer feel all right? Okay. So that is the coordinate point form of the final answer. That is the location of the end of that green arrow. But that's only one way to write a vector. That's the component form. There is also separately magnitude and direction form. I want to make sure you guys are able to do that too, so we're going to take this answer and turn it into magnitude and direction form. By which I mean, just going to redraw that dotted green line. That 40 and that 15 can be thought of as the legs of a right triangle, where the hypotenuse and that angle are the magnitude and direction form. So the 40 and the 15 tell you coordinate point final location and form the legs of a right triangle, where hypotenuse and this angle represent magnitude and direction, where if you had a tape measure and a compass instead of a coordinate point system, you'd know, put one end of your tape measure here, point your compass in this direction and walk so far here and you'll find the football. So we're going to take our coordinate form answer and use trig to turn it into the other way to write a vector. So kind of the reverse of how we began the Cannon problem a second ago. That one we began with magnitude and direction and turned into components. Now we're starting at the components to turn into the magnitude and direction form. Questions about that basic setup? Or at least the notion of what we're doing. All right. So, we need to know the hypotenuse of this triangle, and frankly at this stage there's multiple ways you can get to the correct answer for both the hypotenuse and the angle itself. How would you think to find the hypotenuse of that triangle?
Pythagorean theorem.
Pythagorean theorem. If you haven't called it by that name in a minute, that's referring to this formula, which relates two legs of a triangle to the hypotenuse. C is always the hypotenuse. So in this particular case, that's going to be 40 squared plus 15 squared equals height squared. Hypotenuse will then equal the square root of 40 squared plus 15 squared. And if memory serves, that's 42.7 yards. That's the third side of our triangle. That is the distance in a straight line that the ball lands in comparison to where it starts. That is the length of the dotted green line. So lastly, we just got to figure out what direction this vector points in. The angle is always the direction. And for this one, we can turn our attention to SOHCAHTOA, because Pythagorean theorem can't tell you an angle. And quick review, from this unknown theta's perspective, which of the two legs is opposite? Very good. I usually like to draw out the line to make that clear. So 15 is going to be op, and 40, by process of elimination, is going to be adjacent. And since we know all three sides, you can really pick any trig function here. It doesn't really matter, because whatever one you pick is going to have two sides in it. You know both of them, and it's going to help you get theta, which is what we want. So when you have all three sides, any trig function is on the table. I like to use tangent in this case, because the 15 and that would use the 15 and the 40, and those are nice rounded numbers. So tangent is TOA, tan opposite adjacent, 15 is the opposite, 40 is the adjacent. So how do you break down a tangent to free that theta? Very good. We're going to do inverse tangent to both sides. That's going to break down the tangent on the left, leaving us with just theta, which I will write out. Just theta equals inverse tan of 15 over 40. So this is just the way that you send the trig functions over. And if you correctly hit the inverse tan function on your calculator, plug 15 over 40 into it, and if your calculator is in degrees mode, what angle should that give us? 20.7, I think I heard. Oh, 20.5. I'll round that to 6. 20.6 degrees. Is that right? Well, my hearing's not great. I want to make sure I heard that right.
Yeah.
All right. So, the magnitude and direction version of our final answer for where does the football end up is 42.7 yards at 20.6 degrees. That is the second way of writing this answer. And it's very important to be able to take one and turn it into the other. How you guys feel? All right. That's pretty much everything I wanted to cover for today. Any questions at this particular time? All right. We're well and truly into 2D motion at this point, which is technically chapter 3 material. So I do recommend looking through the chapter 3 stuff when you have time for it. We'll call it here for today, because I don't want any of my lectures to get ahead of any of the others. But I'll just show you. On Friday, we're going to practice all of this for weirder scenarios, weirder cases of vector addition. So that's next time. I promise I'll make it make sense. Any questions for right now? All right. Let me know anything you guys need. Bring your projectile and 2D motion notes to lab this week if you haven't had it yet. And have a great day.